So OpenVSP obviously has a bunch of built-in components, things like pod, wing, fuselage, stack, but it also has the ability to write your own custom components and define your own. And the way this works in general is an advanced user, somebody who knows what they're doing, writes a VSP script file. So they write this custom component, and it's written in AngelScript, the same scripting language that we use for advanced links and that you can use for the API. And it's basically a C or a C++ like syntax, and it has OpenVSP methods that are also available for that. Once you've written that file, you place it in the custom scripts directory. Now, VSP actually searches for 3 places for custom scripts when it starts up. It searches the custom scripts subdirectory in your home directory, in your working directory, and in the directory where the VSP executable is located. So you can use that to your advantage. If you place your custom scripts, well, there's some that come with VSP, and those all go in the executable directory. So if there's some that you want to, go with the version of VSP that you're using, you can place them there. If there's some that you always want to have available on your computer, then you put them in your home directory. And then whenever you run, it'll find those custom scripts in your home directory. And then if there's some that you only want to be in a single project, then what you can do is run VSP from that working directory. And then if you have those custom scripts in that working directory, it'll only find those. Once you've added a custom geom to a model, you don't have to worry about copying the custom script around with it. We actually embed the entire source code for that custom script in the VSP3 file. So you don't have to carry along any other files in order to share that model. That said, you have to be careful, because if you have some proprietary information, say, a sizing relationship for, a SATCOM antenna, and you build that proprietary information into an advanced link because you wanted to be able to, or into a custom component because you wanted to be able to size the SATCOM antennas using your proprietary information, anybody you send that VSP3 file to gets those equations, right? It goes with it. So it shouldn't be a problem, but just know what you're doing. Now, if you ever want, there's actually the ability, if you do have a model that has a custom component in it and you've lost that VSP3 file, that VSP script file, or somebody sends you one and you're like, wow, I really want to use that VSP script, but I don't want to use the rest of their model, you can actually extract it. You can actually take it out of the VSP3 file and save that script to the hard drive. Now here it talks about model exchange via the hanger. That's obviously out of date. Now it's the VSP Airshow. So the easiest way, if you have a custom script and you want to share it on the Airshow, all you have to do is add that custom script to a model and instantiate it so that you just have a model, a VSP3 file that all it contains is, say, your custom SATCOM antenna, and then upload that VSP3 file to the Airshow, and it's a great way of sharing a custom script. So the simplest possible script, all you really have to do is implement 4 methods. And this is the complete source code for an example script of a cone. And I say you have to implement 4 methods, but one of them is actually empty. So really you only have to do 3 methods. And you can do things a lot more complex, but to start with, this is all it really takes. I'm going to go through each of these methods one by one. So first, there's an init script. And it says right up here in this comment, and it is called once when the custom geom is constructed. So that sets up the parameters, basically. So this cone was parameterized by height and diameter. And so it actually goes in and declares these variables and sets up these params. So we're going to add a parm that's called, that's the height parm, and we're going to add a parm for the diameter parm. We're going to set the limits in the description to those. And that's really the setup that we need to do. Each of the actual geometry underlying a custom component is what we call an XX surf. So it's a series like a stack or a fuselage or a wing. It's a bunch of cross sections, one after the other. So in this case, we're going to set this up. We're going to set up the XX surf, and we're going to set it up as being a point, a circle, and a point. So we're not assigning any values to those, but we're just setting it up saying, okay, this is the topology of how our execsurf is going to work. And that's all you need in the init script. And again, it runs once when you instantiate a cone, custom cone. You also need an init GUI, and this similarly runs once when it's constructed. And this GUI is just going to set up this design tab. So we add the tab, we add a little Y gap, this space at the top, we add a divider box, this blue bar that says design, and then we add two adjustable sliders. We add the height slider and the diameter slider, and that's it. We've just added and created a GUI for our custom component. And again, this is only called once, it just sets up that GUI. We have the optional method to update the GUI. Now, in our case, updating sliders is taken care of automatically, so we don't even need an update GUI method. If you do some things more complicated, and I'll show you some examples of that later, then you might need an update GUI. But for most folks, if they're doing simple custom components, they don't even need an update GUI. Finally, where all the real work happens is the update surf method. And this is called every time somebody moves one of these sliders. Every time the geometry is updated, we're going to come in and update the surf. And this is where you do the math to tell it how to take these parameters, the height and diameter in this case, and convert that into the settings for that execsurf that I was talking about a minute ago. And so you can see here, we're going to get parm, we're going to get the diameter and put that into a diameter value, into a double. We're going to get our execsurf, we're going to get our circle diameter. When we get our execsurf, we're going to get section 1 and section 2. And it starts counting at 0, so 0 is the point. So we're going to get section 1 is going to be the circle and 2 is going to be the closeout point. And then we can go in and we're going to find what's the parameter for that cross section of the circle diameter, and we're going to assign that value, and we're going to use that, and we're going to set the cross section location. So we're going to set the location of that second cross section to be the height value away. So we've just basically applied what we needed to the exec curve, and then the last thing we do is we tell it to go ahead and skin that execsurf. So take that and loft the space between the cross sections in order to generate a shape. And that's all it takes. That's the entirety of the code that's needed to make a custom component for a cone. Now, people have made lots of cool things with these, and I'll show some demos. Over the years, you know, JR, Jim Fenbert, my former student, Michael, a couple of folks who work at NASA, Nat Blasser and Natalie Breton, who's an intern there, have written some really amazing different custom components. You know, with distributed propulsion components, some landing gear components, a gun component, a reentry capsule, a missile-like component, a separate flow turbofan, and for those of us who recognize this, the SGI logo, you know, just because we can. One thing that's interesting, and this transport fuselage here in the middle. One thing that's interesting is you may notice that a lot of custom components, people end up using more than one surface, right? In normal geometry, when you add a pod, there's just a single pod, a single surface that then gets copied with symmetry. Or a wing, there's a single wing that gets copied for symmetry. Whereas it turns out it's very common. For example, this gun is made with 1, 2, 3 discs. There's an ammo can, there's a breech, and then a variable number of barrels out the center. And so each of these is then a separate execsurf, and you end up with a lot of multi-surface geometries, which is an interesting use case that that people really made use with. The same thing with this missile. You know, each of these fins is a separate surface from the body. So those 4 methods are the only required methods. And again, one of them can be empty and frequently will. There are a couple of optional methods that I will encourage you to use. One of them is the scale method. If you want your component to be able to scale using the scale slider on the Xform tab, then you need to tell VSP how to behave from that scale parameter. And what this really means is, you know, you might implement, for example, you might have implemented a cone. Instead of telling us the height and diameter, you might have specified the height and then the diameter to height ratio. And if you do that, the diameter to height ratio is now a non-dimensional variable. And so it does not need to be multiplied by the scale factor. So if you're changing something from feet to inches and you need to multiply by 12, then you don't need to mess up to multiply the height to diameter ratio by 12. You only need to multiply the height by 12. So that's really what you're doing in here, is you're coming in and you're telling VSP how to scale or not all of the parameters, and you just need to come in and get the scale value, which is passed in as an argument, take that, multiply it by, and then set those parameters. You also have an optional method that you can implement, which sets the rotation origin. So you may have noticed on components, on the Xform tab, there's this rotation origin in the X direction. And this is a slider that's sort of 0 to 1, and typically it's along the representative length of the component. That's going to be the root chord of a wing, that'll be the length of a fuselage, but whatever that means is different from component to component. And what we're doing is we're shifting that rotation origin along that axis. And so Compute Center does exactly that. We're setting a custom center point in XYZ based on the parameters. And so we take in what is this origin value, right? We're taking in the origin value, and we're using that to decide where we're going to rotate the cone about when we need to rotate about its center. So here, that means sets up 0 to 1, scales along the height in the x-axis, and that way a cone will rotate the way you want it to. So if you want your component to behave in a certain way according to this rotate origin parameter, then you need to implement Compute Center. There's one more set of components that you can implement, which is this setup default sources. And what that does is if you're using CFD mesh and you want there to be, there's a button in CFD mesh that will add default sources to a component. For example, on that engine inlet, on that mixed flow turbofan engine that Nat worked on, you might want to have a ring of sources around the leading edge or around the trailing edge of that duct. And so if you come in and you write a routine for set up custom default sources, anytime somebody's in the CFD mesh GUI and they choose your custom component and they say add default sources, it's going to add whatever sources you tell it to, point sources, line sources, and box sources. And it'll not only position them in 3D space according to your instructions here, it'll even set their size. So if you know there's some criteria about your model, like a trailing edge thickness, and you then want to set the sources so that the edge length is based on that trailing edge thickness, you can do that. There's a couple of special behaviors that you have the option of setting if you want to. One of them is you can set the type of the surface. And so VSP has 3 surface types. There are normal surfaces, wing surfaces, and disc surfaces. And basically, these are the information that we use when we create a VSP aero model, where a wing type surface is going to have a kata condition applied, and that will become a lifting surface. A normal surface does not, and that's going to be a fuselage. And then a disc surface is going to be a thin surface where an actuator disc will be placed. So if you want to build your model like that distributed propulsion thing that had a bunch of actuator discs, you can do that. Or if you want to build a bomb or a missile that has some fins on it and you want the body to not carry lift, but you do want the fins to be lifting surfaces, you can come in and you can tell it that the fins are wing surfaces and the body is a normal surface. Somewhat similarly, there's something that we call the CFD surface type, and that's really a flag where you set whether a component is normal or negative. So if you wanted to use negative volumes in your custom geometry, you can come in and you can make one of the surfaces and you can set it to be negative. There's a couple of other variables you can set here, and the names are a little weird, but they're basically called transparent and structure. And those are used for non-watertight components, things like an actuator disc or a rib inside of the air or inside of the wing. And those are thin, typically thin membranes that don't enclose a volume. They're not watertight. And then the reason they're different is basically a structure thin membrane, which would be like a rib or a spar. We expect that to be inside the aircraft. And when we perform an intersection calculation with it, we're going to keep whatever part of the plane is inside the aircraft, and we're going to throw away whatever the part of that plane that surface is outside the aircraft. Conversely, a transparent component behaves the opposite way. That would be like an actuator disc, which is outside the aircraft. And any of the actuator disc that overlaps with the airframe, we're going to trim and throw away anything that's on the inside, and we're going to keep whatever's on the outside. So what we're really doing here is we're specifying how we trim that membrane component. And those are the two conventions that you might use. Either way, when you have one of these thin membrane components that has no interior volume, just know that those components do not trim solid components. So like if you put a rib component inside of a wing, that rib will not affect the wing. It won't slice off part of the wing because you can't do an interior check. There's not an inside or an outside of a rib the way there's an inside or an outside of a fuselage. So those are some special behaviors that you can set up if you want to. They're not required, but those things are all available in custom components. And so let me just do a quick demo. We'll just run VSP, and I'll show you some of these, and maybe I'll even show you some code for one. Now, when you run VSP, you may have noticed that some components are in all caps above this horizontal line in the geom pull down. So all the ones that are in all caps above that line, those are built-in components. Those are things written in C++, usually by me, that are distributed with VSP, and they're built in, and everybody's going to have those. Everything below that line, and typically they'll be in lowercase or mixed case, these are all custom components. And you'll see that I have a bunch because people send them to me. I haven't written all these, but other people have. And so all of these are different custom components that are found somewhere on my hard drive. So just to start with, if this is the VSP distribution, you'll notice here's the custom scripts directory. If we come into the custom scripts directory, you'll see a few: box, cone, disk, duct, seat, transport. These are all custom scripts that come with everybody's distribution of VSP. Everybody gets these. If I go to my home directory, RA McDonough, and here's a custom scripts directory, you'll see I'll open these up, and this is where I put all the rest. These are where I put all the ones that other people have sent to me that I might want to use, but that I don't distribute with VSP because they're not mine. And so these are all of these other ones that get located in here. So we can come back, and we can very easily just come, and we'll start with the cone, because why not? It's all the way down here at the bottom, and we'll add a cone. And you'll see here's that cone. It's just the simplest custom component there can be. Again, on the design tab, all there is for this cone is the height and the diameter of the cone. And let's see if this version has the scale parameter. Let's scale it by 2. Oh, it did. See, it scaled by 2. So that was us applying that scale parameter. And likewise, if we want to rotate this about, well, let's rotate. Let's get ourselves with the, there we go, the X pointing down and Z up, just so that we kind of are oriented. So we want to rotate it about the Y axis. Let's rotate it 30 degrees. We can then change the rotation axis, the rotation point. So right now we're at 0, it's right there. But if we change the rotation point, you'll see, oh, this one does not have the rotation origin implemented. So I don't have that in this version of the cone. So that's doing nothing, but the scale is working. Okay, so that's a cone, and everything else in the component, you know, the tessellation, coloring it, right? Everything else about this component works the way you would expect, right? It's just another VSP component. You can attach things to it. For example, if I want to put a pod and I want to make that a child and attach it to it in UV coordinates, I can do that. And when I then move that pod along, right, it's attached to that cone. And like I said, everything just works so that, just like any other component in VSP. Let me show some of these more complicated ones. To start with, I want to show, for example, it's got a lot of components. So here's that gun that I was showing that Michael Waddington did many years ago. And the reason I wanted to show this was first because it uses multiple surfaces, right? This uses a whole bunch of surfaces. And when you come into design, it actually has the ability to change some of these things as discrete variables. So it's parameterized. For example, this is a 6 barrel, but if you want to make it a 7, 8, however many barrel gun, you can change the number of barrels. You can change the caliber. So that's going to be the diameter of the barrel. You can decide whether or not to have an ammo can. So you can actually have discrete variables that turn these surfaces on and off, as well as, as well as continuous variables that you move around, more like normal variables that you're used to with sliders. So that's one thing you can do. He's also gone and implemented this where there were some presets. So here, for example, if you know that you want to model something with a GAU8 and A10 with a circular ammo can, and your model is in units, you dial that up and then you hit go, and it sets those parameters automatically. And this is just because he's built in basically some defaults to match what that behavior is. So that's kind of, some more advanced things that you can do. Let's see, what else do we have? We have a really nice, there's that separate flow turbofan model that Nat and Natalie worked on. So here, and actually I'll make it shaded and transparent so you can see the insides. So here it is with the, the inlet face, and then we have the bypass exhaust and the core exhaust with, separate trailing edges, which have some finite thickness to them. And then this is parameterized. It has 3 tabs. So we have the engine tab, which is just the big picture things, length, diameter, and then the fan. We have the nacelle, which controls sort of the outer shape of the nacelle. And then we have some tangent strengths to continue to control how smooth and how rounded the shape is. So you can do lots of different things here. I think that's probably enough of an idea. Some of my favorites in this, I guess I'll just say, are actually really the simple ones. And I think, let me show you this one just as an example. I'll show 2 of these as examples of how a really simple component can be really powerful. But as it turns out, this transport fuselage shape, it's parameterized just in terms of the length, the diameter, and then here's sort of the most interesting thing to me is this nose multiplier multiple and aft. And so what this is I did some digging and I found that 1.5 times the diameter is often how long the nose on a transport airplane is, and this tail cone is often about 3 times the diameter. And so by setting these as parameters that, number one, match the intuition of the engineer, the engineer who's designing this may think in terms of that diameter ratio. Number one, setting that in terms of their intuition matches the use case and captures design intent in this model. But it also makes it so that, we really only have 2-dimensional parameters here. We have the length of the fuselage, right? And when I'm changing the length, since those are parameterized by the diameter, we're essentially adding a plug or making a short version of the aircraft without having to change that tail cone. And then we can come in and we can say, okay, no, it's not an aero body, it's a wide body. We can come in and increase that diameter and then increase the length to capture whatever fuselage we want. The other parameters here are just sort of tweaking, how drooped is the nose, and then back here on the aft end, how high up is the tail, and then that tail closeout, how wide and how tall is it. So we're able to capture, a large family, a broad family of transport fuselages with only 8 parameters and really own 2 primary parameters, and the rest can often be set at some fairly reasonable defaults. So this is a case where a custom component is able to capture, a very large design space for transport fuselages with a very simple set of parameters. So that's one case that I really like. The other one in here is the capsule. There it is. And it does something very similar. So this is a reentry type shape, an Apollo or Mercury or Gemini or whatever type of capsule that you want. And this one is parameterized just in terms of 5 parameters. So we have the height, which is the overall height, and the overall diameter. So those are your 2 biggest things. And then we just have a couple of radii. We have this nose radius up here. We have the heat shield radius. Oops, that was the nose again. We have the heat shield radius down here on the bottom. And then we have that edge radius, which is sort of the blend between them. And so with just 5 very simple parameters, we can actually capture a huge variation in reentry vehicle type shapes. And so if you're someone who's doing, thermal analysis of reentry vehicles, this one component will let you capture a whole bunch of those. I have the ability, I can show you guys some of the code on these. I don't know which one anybody would want most. We already showed you well, I don't think that there's a lot of benefit in that. There's all of the components that come built into VSP. You can look at the code there and look at those as examples. And I think that just to finish off, I'll show the SGI logo just because it's fun. So let's shade that and view it left ISO, or let's see, where's the right viewpoint for that? There we go, something like that. We can look at that shape. But so you can do a lot with custom components. You can build design intent, domain specific knowledge. If you work with something where you use a certain category of shapes over and over and over again, then writing a custom component of just that shape may be a great way for you to build that design knowledge into your model and then share that model with your colleagues with a reduced parameterization and a tailored parameterization to exactly what you want. So a good question. If you have a multiple XX surf geometry, something like, well, in this case, we'll do it with the gun again, just because I know that one is the case. In this case, if you then attach to it in UV coordinates, let's attach a pod. And we want to come in and attach it in UV. What it does is attachment only knows about the 0th surface. If this becomes a problem, I can add a parameter to attach to a higher numbered surface, but attachment only knows about the 0th surface of a thing. And so in this case, it looks like the 0th surface is, I guess, this little bolt that connects these 2 things together. Let me move the U along here. Yeah, so the 0th surface is, oh no, it's actually that plate. This plate up here at the front, the way this model was built is the 0th surface. So yeah, if somebody needs to attach to different surfaces of a custom geom, and that's a big problem, then put an issue report as a request on GitHub, and I'll see about adding that. Otherwise, just know that when you build your component, you're probably always going to want to attach to the same part, and so make whatever part you want to attach to the 0th surface. Great.